The Purdue Enterprise Reference Architecture is an industrial architecture model that organizes systems according to the functions they perform, from the physical process through control and operations to enterprise planning. In security discussions, the term Purdue Model usually refers to this layered view of an industrial environment. The model gives engineers, operators, architects, and security teams a shared vocabulary. Instead of describing a network only by subnets or vendor products, teams can discuss where a function belongs, what it depends on, and how close it is to physical control. A controller at level 1 has a different operational purpose and consequence than an enterprise application at level 4. OT security practitioners use the model to reason about trust boundaries, communication paths, access, monitoring, and incident containment. It helps expose questionable architecture. For example, a user workstation should not normally communicate directly with a field controller simply because both devices use Ethernet. The Purdue model is not a product, a protocol, or a complete security design. It does not prescribe every firewall rule, and assigning a system to a level does not make that system secure. The model must be combined with asset inventory, current diagrams, operational requirements, risk analysis, and engineering judgment. Modern environments also include cloud analytics, wireless devices, vendor platforms, remote operations, and industrial Internet of Things systems that may not fit neatly into a simple stack. Use Purdue as a reference for asking better questions, not as a perfect map that forces every architecture into identical boxes. The Purdue model matters because industrial operations depend on several kinds of systems working together. Enterprise planning may create a production schedule. Site operations translate that demand into work. Supervisory systems provide operator visibility, controllers execute logic, and field instruments interact with the process. A failure or compromise can move through these dependencies even when the systems belong to different teams. Placing functions into levels helps identify where connectivity should be limited. Traffic that stays within a control area has a different purpose from data being transferred to enterprise analytics. The model supports segmentation by showing where trust changes and where controlled intermediary services may be appropriate. It also supports risk analysis. Systems near the process may have direct safety and reliability consequences. Systems higher in the architecture may have broader user populations, internet dependencies, and exposure to common enterprise threats. Neither is automatically more important. Their risk comes from different functions, pathways, and operational effects. The model improves communication between disciplines. Security teams can explain why direct enterprise-to-controller access creates risk. Engineers can explain why a control flow requires low latency or high availability. Operators can identify which systems provide essential visibility. These conversations turn an abstract network diagram into an operational architecture. Finally, Purdue helps distinguish data flow from control flow. Production data may move upward for reporting, while commands, recipes, or configuration changes move downward under stricter authority. Reviewing both directions reveals remote access, update, and administration paths that a simple data flow discussion might miss. The goal is not to prevent communication, but to make every cross-level flow necessary, controlled, observable, and owned. Level 0 represents the physical process itself. It includes the equipment and conditions being measured or influenced, material moving through a line, water in a treatment stage, power flowing through a substation, or temperature inside a vessel. This is where digital decisions become physical outcomes. Sensors and instrumentation report process conditions such as pressure, flow, speed, position, and temperature. Actuators create physical change. They open valves, start motors, move mechanisms, or operate breakers. A false measurement or incorrect actuation can affect product quality, equipment, safety, and the environment. Level 1 provides basic control. Programmable logic controllers, remote terminal units, distributed control components, and other controllers read inputs, apply control logic, and update outputs. Many perform this work continuously and within strict timing requirements. Their configuration, logic, and communication relationships are operationally sensitive. Security at these levels must respect safety and reliability. Aggressive scanning, untested endpoint software, or an unexpected restart can interfere with deterministic control. Protection often relies on physical safeguards, restricted access, network isolation, authenticated engineering workflows, configuration backups, change control, and monitoring at nearby network points. Level 0 and Level 1 also remind analysts that a device's consequence cannot be inferred from its size or operating system. A small controller may influence a critical process. Risk assessment should identify what the device controls, what independent safety functions exist, how loss of communication affects the process, and how trusted operation can be restored. Level 2 contains the systems that provide supervisory control and visibility for a process area. Human-machine interfaces, local operator stations, alarm services, and area-level control servers are commonly associated with this level. They translate controller data into information that operators can understand and act upon. An HMI displays measurements, equipment state, trends, and alarms. Depending on authorization and design, it may also allow an operator to start equipment, acknowledge alarms, adjust a set point, or select an operating mode. The HMI does not replace the controller's real-time logic, but it can influence how that logic is used. Level 2 compromise can affect operations even when field controllers remain intact. Operators may lose visibility, see misleading values, miss alarms, or issue commands based on untrustworthy information. A widespread workstation outage may cause a facility to enter a safer manual mode or stop production because continued operation cannot be supervised confidently. Controls should protect both availability and integrity. Limit administrative access, separate engineering privileges from routine operation, maintain recoverable configurations, monitor communications with controllers, and restrict pathways from higher levels. Endpoint protections must be tested so they do not disrupt required applications or introduce uncontrolled reboots. Incident planning should define how operators recognize loss of trusted visibility, what local indications remain, and which actions are safe. Level 2 shows why cybersecurity cannot focus only on whether control logic was changed. Reliable operator awareness is itself a critical control function. Level 3 supports site-wide operations and coordination across production areas. Common functions include operations management, manufacturing execution, batch or recipe management, site historians, engineering services, OT administration, and other systems needed to run the facility as a whole. A historian may collect process data from several areas for trending, quality analysis, reporting, and investigation. A manufacturing execution system can coordinate work orders, materials, and production status. Batch systems manage recipes and sequences. Engineering workstations maintain controller logic and device configurations. These functions have broader scope than a single HMI or controller. Level 3 systems are often conventional servers and workstations, but their operational context changes their risk. An engineering workstation may have authority to modify many controllers. A compromised operations server may disrupt coordination across several lines. A historian can become a pathway toward lower levels or a bridge toward enterprise consumers if its connections are not controlled. Security priorities include privileged access management, secure administration, application allow listing where appropriate, tested backups, patch planning, centralized logging, and segmentation between production areas and higher-level networks. Service accounts and vendor tools deserve particular attention because they may have broad and persistent access. Level 3 is also a natural place to coordinate monitoring and response. It can provide context about production schedules, engineering changes, and expected traffic. During an incident, the organization must understand which site services can be isolated, which are required for safe operation, and how lower-level control can continue if site coordination is degraded. The industrial DMZ is commonly described as Level 3.5. It is a security extension to the traditional Purdue discussion, not an original numbered level. Its purpose is to create a controlled buffer between enterprise IT and site operations, so ordinary enterprise systems do not communicate directly with control networks. Services in the industrial DMZ mediate necessary exchange. A jump host can provide a managed path for administration. A remote access broker can enforce identity, approval, and session controls. Patch and antivirus repositories can stage content before it enters OT. Data replication services can move historian information outward without allowing enterprise clients to query control systems directly. Monitoring, logging, authentication proxies, file transfer services, and update gateways may also belong in this zone. The exact design depends on operations, but each service should have a narrow purpose. Connections should specify approved sources, destinations, protocols, direction, and owner. Broad routing through the DMZ defeats the reason for having it. The DMZ is not automatically trusted. It faces connections from two environments and may contain high-value access services. Harden systems, separate administrative access, monitor traffic, patch deliberately, retain logs, and avoid using the zone as a general-purpose server network. Remote sessions should terminate or be proxied there rather than passing transparently into OT. A strong industrial DMZ reduces direct enterprise-to-control connectivity and creates inspection points for data and control flows. It cannot repair weak segmentation below Level 3 or poor identity governance above it. Think of it as one architectural layer in a broader defense that includes controlled pathways, least privilege, asset knowledge, and operational oversight. Levels 4 and 5 broadly represent enterprise planning, business systems, corporate users, and external connectivity. Organizations describe these levels differently, but common examples include enterprise resource planning, corporate identity, finance, email, user workstations, data platforms, internet services, and cloud connections. These systems support the business around production. They create schedules, manage materials and orders, provide workforce identities, and consume operational data. Because they serve many users and connect to external services, they are exposed to common enterprise threats such as phishing, credential compromise, ransomware, vulnerable applications, and third-party access. Enterprise compromise can create OT risk through shared dependencies. A corporate identity outage may affect authorized remote support. Ransomware may disrupt production scheduling or files needed by operations. A compromised user account may reach a poorly controlled jump host. A cloud integration may create a path that bypasses the intended industrial DMZ. The Purdue view helps teams resist direct connections that are convenient but unsafe. Enterprise applications should exchange required data through controlled services. Corporate users should not administer controllers directly. Identity and remote access designs should preserve strong governance without creating a single unexamined dependency for critical operations. Security teams should map cross-level business flows, including scheduling, reporting, support, updates, and authentication. For each flow, identify what happens if it is unavailable, altered, or misused. Enterprise and OT teams share responsibility for these boundaries. Protecting Level 4 and Level 5 is part of OT risk reduction because the enterprise environment often supplies the pathways, identities, and services that connect to operations. Applying Purdue begins with reality, not a blank diagram. Inventory assets, document their operational functions, and map actual communication paths. Then assign levels where the model clarifies responsibility and trust. If a system performs several functions or crosses levels, record that complexity rather than forcing a misleading label. Use the model to design segmentation. Group systems with compatible functions and consequences, place controls at meaningful boundaries, and permit only required flows. Remote access should enter through managed services, not bypass levels. Administrative paths deserve the same scrutiny as production data because they can change configurations and logic. Purdue also guides monitoring placement. Enterprise boundaries reveal attempted movement toward OT. The industrial DMZ provides visibility into cross-environment exchange. Site and control area monitoring can identify new devices, unexpected protocols, engineering activity, and changes in normal communication. Monitoring choices must account for sensitive devices and operational traffic. During incident response planning, use levels to identify containment options and dependencies. Blocking a boundary may protect lower levels, but it may also interrupt identity, reporting, or support. Plans should distinguish which functions can continue locally, what visibility remains, and who can authorize isolation or shutdown. Modern cloud, industrial Internet of Things, mobile, and vendor services challenge a simple hierarchy. Some devices communicate directly with cloud platforms. Remote operations may span sites. Software-defined infrastructure can shift functions dynamically. Extend the analysis with data flow diagrams, identity architecture, trust boundaries, and environment-specific threat modeling. The model's value lies in disciplined reasoning. It supports segmentation, access control, monitoring, inventory, and response, but it does not replace them. Validate every conclusion against the actual process, architecture, and operating constraints. The Purdue Model is a practical reference for understanding industrial architecture. It organizes functions from the physical process and basic control through supervisory and site operations to enterprise systems. The industrial DMZ adds a control buffer for necessary exchange between OT and IT. Each level has different responsibilities and consequences. Lower levels interact directly with equipment and require careful attention to safety, timing, and reliability. Supervisory and site systems provide operator visibility, engineering authority, and coordination. Enterprise systems create business dependencies and potential pathways toward operations. Use the model to improve asset inventory, segmentation, access control, monitoring placement, remote access design, and incident planning. Review data moving upward and commands, configurations, and administration moving downward. Make cross-level communication necessary, limited, observable, and owned. The model is not a perfect map or a substitute for engineering. Cloud platforms, industrial Internet of Things devices, vendors, remote sites, and converged architectures may cross traditional levels. Current diagrams, operational knowledge, and environment-specific risk analysis remain essential. The strongest use of Purdue is shared reasoning. It helps security, engineering, operations, and business teams discuss how systems depend on one another and where controls should protect physical operations. Let the model guide questions and architecture decisions, while letting evidence and operational judgment determine the answer.